All right, everybody, lecture 28, let's get started. I mean, we only have, 40-some lectures, like I think it's 43, and that includes, exam review and exams, and we are much closer to the end of this class than we are the beginning. To put that in perspective, so we are on Centroids 3. We have 5 lectures on this module. So after this, we do structural analysis. We have 4 lectures on structural analysis. We have 2 lectures on friction. And then the only thing we have left is exam 3, the final, and then the review that we do at the end. And that's it for this whole class. So we really are winding it down in a very real way. In terms of housekeeping, I am still working on the exam. My goal is to get that back to you either Monday or Wednesday of next week. So I don't foresee any real issues getting it to you by then, although I'm starting to get some stuff stacked up on my desk, so I kind of need to start knocking it out. Homework 5.2 was due. How did the Centroid homework go? Was that hopefully a lot better hopefully a lot better, but I imagine it was much more straightforward than homework 5.1. The homework 5.1 was the calculus one. This one's very plug and chug. That algorithm that we discussed, the idea of breaking a shape up into simple shapes and doing this weighted average approach, we are going to be doing this not only for the next few lectures in here, but this is the, you're going to be, again, as I said last time, you're going to be computing centroid locations throughout the entirety of engineering. So it's an incredibly important skill to be able to master. And so what we're going to do is we're going to expand upon that skill by looking at things a little bit of a different way. So just to sort of set the stage for what we're going to talk about today, so and I'm just going to use X bars here for the discussion. So X bars would be, I'm looking here at sum of XA over sum of A. So basically what this is saying is if I have some arbitrary region, I can determine where the centroid is, right? And the algorithm to do that is this right here, okay? So, but this process and this idea can extend to other geometries. For example, what we're going to do today what about considering lines and curves, okay? So an example might be, how many of you have ever seen a house being constructed and you see them lifting the wooden roof trusses up maybe on a little crane to start erecting the roof, right? So we have this, a roof truss, right? And maybe it looks something like this, something like that, right? And how do I find the centroid of that, okay? Well, maybe what I'll do is this, where the X's are the center of each of these line segments, And so I can find the centroid of a line group. And this is an example. Another example for you mechanical folks might be locating the centroid of a group of welds, like welding, 2 pieces of metal together. Another more direct application, which I think would apply to anybody in this room, is what about considering volumes, okay? And trying to find the location of a 3-dimensional body, right? So imagine I have a, imagine I had a body like that, like a prism with a notch cut out of it. Where is the centroid, How would I do that, Maybe I'll put a hole in it right here and a hole in that face. How do I do that, How do I compute the location of the centroid? Well, same idea. Break it up into simpler components or simpler regions. So maybe I have a rectangle, a triangular prism, a cylinder, and what have you. So again, a lot of the same ideas, okay? So that's sort of what we're going to be doing over the next few lectures, is really just trying to cement the idea of, extending our definition of centroids to make sure that we're comfortable with looking at them. We're also going to do a little bit of another application of centroids, bless you, looking at distributed loads. And we'll talk about that later. Okay, so last time we sort of, started with this. And again, when we derived the expression for the centroid, we started with sort of a weight perspective and then sort of generalized that to looking at areas. And then we broke out the idea of these centroid references, which we're not going to use these today, so I'm just going to sort of gloss over them. But we will use the B8 or B over 3 and H over 3 for a triangle, but I'll just assume we can remember that one. Today what we're going to do is look at centroids of lines and curves. And so if I'll say this, to be honest, we're really not going to look at the centroid of a curve. We're going to mostly look at straight line segments here. But the idea is that if I had some sufficiently one-dimensional object, maybe like a wire or a weld group or trusses or what have you, and I wanted to find the centroid, I could do it in this fashion. I could do it in this fashion, or I could do it in terms of integration. And the integration would probably be more appropriate if I had a curved segment. I mean, I could take a curved segment and approximate it as a series of straight line segments, and so the more approximations you do, the better you get at it. But again, the idea is the same. Instead of integrating or summing in terms of area, we're doing it in terms of length. Okay? And so just to get right into it, I want to look at the following example just to make sure that we're comfortable with this. So what we're going to do is we're going to compute the centroid of this wire group. Okay? Now, I want to be clear that on a couple things. First off, we are not going to get the same answer as B over 3 and H over 3. We're not going to get that because this is not a solid triangle. This is a series of 3 wires, okay? And we're trying to figure out the center of this group of wires. So instead of like a solid triangle, sort of think of like trying to find the center of a hanger, like a clothes hanger. Like where is the centroid of that, okay? The other thing that's worth mentioning is I don't really like this diagram. I like it because it shows that it's a wire, but I don't like it because it has these rounded segments here. But for the purposes of our discussion, we're going to sort of ignore the rounded segments. And so we're going to treat this wire as if it's just, that, and that. Sort of 3 straight line segments. Okay? And what we're going to do is compute the location of this wire group. Okay? Now, one of the things that that isn't on this problem that I think is worth discussing is there is no coordinate system. If you recall the last problem that we did, let's go to that last problem just to refresh our memories. If we go to that last problem, we were given a reference. We were given a coordinate system. Okay, we were given that because this was our first time doing it. So let's put this down here as a frame of reference. However, sorry. Now that we get it, we get the idea. What we have to recognize is that as engineers, that's not really like we're going to have to choose our own coordinate system. Okay. Now, what I'm going to do is I'm going to choose my origin at A. I think that's kind of the natural place to put it. So we'll say this is the y-axis, and this is the x-axis. So that, and the reason I'm choosing that location is that when I compute the coordinates of the centroid coordinates are all positive, right? There is nothing, quote-unquote, correct about that strategy. I could pick the location of the centroid B anywhere, okay? Now, if I pick the location at A, I am going to get different numerical data than, let's say, if Ashlyn picks B, right? But so let's just make up a number. Let's say the centroid this way is 19 inches. So I'm going to get x bar as 19. You'll get x bar as -5, but it's in the same spot. Does that make sense? Okay. All right. So what we're going to be doing is we're going to be using the tenets of x bar equals sum of xl over sum of L, and y bar equals sum of YL, or sum of L. That's kind of how we're going to handle this. Okay? So we've got 3 wires here, 3 of them, and I'll just use their letter designations to keep this easy. So we'll do it the same way that we did it before. I can do better than that up here. Okay. Okay. So the first thing that we'll do is we're going to treat this the same way that we did the last problem. But remember, the first thing that we did was we computed the areas, and then the x and xa, and then y, then ya. Now we're going to do the lengths. So AB is 24 inches. This is 26 inches. This is 10 inches. Okay? Now, I didn't have to do any computation. It's all just measured, right? And by the way, this is a right triangle. Because really what this right triangle is just a scaled up version of 5, 12, and 13. Because 5 squared plus 12 squared equals 13. Pythagorean triangle. Okay. All right. So if I put a summation column down here, the sum is going to be, what is that? 24 and 26 is 50, so that's 60. Okay. So what I'm going to do is, because I think it would be kind of natural, since we're going to compute the whole thing, we do kind of get the algorithm, I'm going to do this. We're just going to do x and y together. So let me ask you a question. Okay, so we're going to do along the x-axis. Okay, but maybe let's be a little bit more general. Okay. The centroid of each of these wire segments, it's just a wire. It's just a straight wire. So the centroid of each individual wire is just in the middle of the wire, right? Okay. So this right here, that little red dot that I put right there, that's the center of centroid of wire AB, right? Help me out. What are the coordinates of that point? 12, 0, right? 12, comma 0. So don't we just put 12, 0 like that? What are the coordinates of, let's do AC, that point? What are the coordinates there? 0, 5. 0, 5. So this is down here, 0, 5. So if that's the case, what are the coordinates of this point? 12, 5, right? Halfway over, right? Because this right here, that's actually kind of a vertical line, and that's a horizontal line. Does that make sense? Past this, I hope that the example is very boring, okay? Because we're going to do this. We're going to do this. Okay? So let's do the XL. Okay? So 24 times 12, that's double 144, 288. This one's going to be 312, and that one's going to be 0. So 288, 312, and 0. And what do we got here? We've got 0. This one's going to be 130 and 50. So let's see, that's 180. And 288 and 312, that's 500 and 100, that's 600. So therefore, bless you. Fortunately, this math is pretty easy. And I guess what I should do here, maybe just to be hyper specific, is to indicate that that is in fact measured from point A. The point A is our origin. Because magnitude and direction, I guess the analogy here is that the coordinates of the location of the centroid don't really matter if I don't know where they're measured from, if that makes sense. And if you notice, this is not quite a third of the way over, right? The triangle had a base of 24 inches, so a third of the way over would be 8. This isn't 8, this is 10, right? And it's 10 inches tall, it's not 10 over 3 up, it's just 3 inches up. Because again, it's not a solid triangle, it's just the wires, okay? Does that make sense? Okay. So far so good? Hopefully this is easy. Okay. All right. Sound good? Okay. I want to turn our attention to an application of centroids that will expand our ability to perform assessments of static equilibrium. Okay? And this is something that I'm just sort of sneaking in, but I'll tell you that most practical analysis problems deal in distributed loads more than they deal in concentrated forces. Now I'm going to give you a civil engineering example, but I'm going to extend it to all areas of engineering. I want to talk about distributed loads, and I'm going to start off with this. Okay? This is a ballroom. Okay? And as we can see in the ballroom, there's a lot of people, right? That's a lot of people. And the floor system has to be able to be strong enough to withstand the forces of all those people. Now, what we do not do in a practical engineering exercise is treat each one of these people as a 150-pound J vector, or here's 150 pounds, here's 120 pounds, here's 190 pounds, here's 220 pounds, and design this floor for about 560 vectors pointing down. We don't do that, okay? But we do have to design it in some fashion. Instead, what we do is we say we're designing this floor system, so we will design it for a generally applied distributed load that would reflect the use of the structure. So I'll give you some numbers to make the point. So if I was designing a floor system for, say, a classroom like this, I would typically design the floor system for around 40 to 50 pounds per square foot. Whereas if I was designing a library, I might design a library for 150 pounds per square foot. Why am I designing the library for so much more load than the classroom? Because the library contains all the books that all the college students don't read. So that was a joke, not very funny. But in all seriousness, the loads that we use would be reflective of the use of the structure. To give you maybe an example that's less humorous, We would design maybe rooms, like let's say hospitals. We might design the rooms for 50 pounds per square foot, but we might design the hallways for 80 pounds per square foot or 100 pounds per square foot. Because by their very nature, a hallway is going to have a higher concentration of people and stuff in it than a room is. Does that make sense? So you would select the load accordingly. So how that would come about on a given beam or a given element in the structure is the element in the structure wouldn't see a 200-pound force or a 2,000-pound force right in the middle of the structure. It would see a load distributed across its length. Okay? So we wouldn't be dealing with like a single point load. We would be dealing with like a distributed load. Okay? Now there are applications of distributed loads in all areas of engineering. A simple example, and again, I know I'm throwing a dam here, but just any hydrostatic force effect is going to be considered a distributed load. So this would be applicable to mechanical engineers, electrical engineers, civil engineers, maybe even you biomedicals. As you are in water, okay, the deeper that you get, the higher the pressure increases, right? Pressure increases as a function of depth, and it's a linear relationship, right? You can calculate the pressure at a given depth by basically just taking the depth and multiplying it by the unit weight of the fluid, right? So for example, if you were 10 foot deep in water, the pressure would be 10 foot times 62.4 pounds per cubic foot, because 62 pounds per cubic foot is how heavy water is, okay? So what the structure would see is a distributed load, but it would be triangular in nature, okay? Now how do we as analysts deal with loads that are not concentrated? Well, the way that we handle them is we sort of turn them into concentrated force effects. Now how would we, for example, how would we turn this triangular load into a concentrated force? Well, what we would want to do is replace it with a single vector, okay? Now, what would the magnitude of that vector be? It'd be the area of the load. Now, where do you think I would place it? What would this distance be? It'd be the centroid. It'd be y up. Does that make sense? So you would go you would place this vector at the centroid up. Why am I placing it there? Because if I place a vector here that has the same area here and place it the centroid up, I propose it has the same static equivalence as the distributed load. And the beauty of that is I know how to solve for reactions and analyze structures for this because we've been doing it all semester. Okay? To make the point of what I'm talking about, I want to analyze this beam. Okay? So let me I want to look at this beam. Okay, so I have a load that is slowly increasing on a beam. Okay, it's going from 1,500 newtons per meter all the way to 4,500 newtons per meter. Okay, and what I want to do is I want to determine the support reactions for this beam. Okay, now I'm going to do this problem two different ways, and we're going to see that either way we do it, we're going to get the same answer. Okay, so I'm going to show you how we're going to do this. I'll call this option 1. Which I'll call components, okay? So let me explain how option 1 is going to work. What I'm going to do is I'm going to take this load, so this is a trapezoid, right? Okay. What I'm going to do is I'm going to treat these numbers, this 1,500 and this 4,500, I'm going to treat them like they're dimensions, okay? So the idea is that, you know, this height, I mean, I'm literally treating it like a height, that height is 1,500, okay? And I'm treating this height like it's 4,500, okay? So if that's the case, what I'm going to do is I'm going to split this like this. So I'm going to have a rectangular load right here, and then I'm going to have a triangular load right here. Forgive me about the scale and whatnot, but you'll see what I mean. So just to make sure we're all on the same page, what is this height right here? Okay, so if this is 1,500, what's this height? 3,000. Okay. So option 1 is going to be to do the following. Here's what option 1 is going to be. Okay, so we're going to have an unknown force. We'll call this AY and BY. I don't know what they are yet, okay? But what we'll do is we'll say, okay, I'm going to use my color scheme. I have a distributed load that's kind of like this, okay? Now that's a rectangle, okay? If this beam is, remind me, this beam is 6 meters long. That's how long the beam is. How far would it be from, we'll say, point A to, we'll call it this point right here. And what we'll say is that this is the centroid of that rectangle. So how far is it from point A to, say, the centroid of that rectangle? 3 meters. Okay? Now, I'm going to call this R1. Okay? So how do I compute R1? Okay, again, I'm going to compute R1 like it's an area. Okay? The magnitude of this force is going to be just that, the magnitude of the force. Okay? And what I'm saying is I have 1,500 newtons per meter acting over a distance of 3 meters. Does that make sense? So this is going to be what? 4,500 newtons? Or wait, no. Not over a distance of 3 meters, over a distance of 6 meters. Sorry. That's 9,000. Okay. Bless you. So the idea is that instead of this distributed load, so on the original structure, I had a distributed load right here that was 1,500 newtons per meter over a distance of 6 meters. I am getting rid of that, and I am replacing it with this single force of 9,000 newtons, and I'm placing that 9,000 newtons right there, 3 meters away. Because I propose that has the same force equivalency. I mean, this is 9,000 newtons, and that was 9,000 newtons. And it has the same moment equivalency because I put it right there. Does that make sense? Okay, so if that makes sense, what I'm now going to do is the same thing. But I'm going to do the same thing with this triangular load. Okay? So I'm going to take the area of that triangular load and I'm going to replace it with another vector. We'll put it right there just to not crowd everything. We'll call that R2. Now a question for everybody. where do I put this? What is that distance from A? 4 meters, because it's a triangle, right? Triangle, it's a third of the way from the right angle or 2/3 of the way from one of the acutes. So now what about the magnitude? What is the magnitude? The magnitude is the area of the triangle. And the area of the triangle is 1/2 base times height. What is the height of the triangle? 3,000. It's not 4,500, it's 3,000. And this also happens to be 9,000 newtons. Does that sound good? No, I'm talking about the entire area. I'm going to use the 3 and the 4 meters here in a bit. In fact, let's talk about how we're going to do that. So here's what I've got going on. Here's what I've got. I essentially have a beam that has a load here and a load here. That's what I have, right? And I'm trying to figure out these reactions. So ignoring all the centroid stuff, if this was point A and this was point B, I mean, I'm asking you, how would you solve for these reactions? What would you do? Maybe some moments at A to determine the reaction at B. Some forces in the y direction determine the moment at A, right? Let's see what happens. So we'll sum moments at A. So tell me what to do. What do we have? R1 times 3 meters. Is that positive or negative? Bless you. If I'm at A. Negative, right? So R1 times 3 meters, negative. Maybe minus R2, 4 meters, right? Plus 6 meters times By equals 0, right? Let's do some substitution. So both of these are 9,000, right? So 9,000 times 3, 9,000 times 4. So this is negative and then that's just going to equal negative By times 6 meters, right? So we got a bunch of negatives in here. Let's get rid of all the negatives. So 27,000 and 36,000 gives you 63,000. Divide both sides by 6. And I'm going to get that. Now, did I do that too fast? You tell me. I'm hoping by now that's simple. Is everybody okay with that? Okay. So now we'll sum forces in the y direction. And let's see what we get here. So if I sum forces in the y direction, let me do this. So I've got AY and BY going up. I've got R1 and R2 going down. Okay, I'm hoping that I was kind of silent while writing all that out, but I'm hoping that that wasn't all that challenging. And we've done that stuff for a while, right? So I don't want this part to be the fuzzy part, okay? But like I said, this is option one, okay? The purpose of this lecture is to explore how centroids can be used in the assessment of static equilibrium. So I'm going to show you option two here in a bit, okay? But before I do, was this okay? Everybody okay with this? Now let me show you option two. And I imagine that some of you can probably predict where this is going, okay? Okay, so option two is going to be to use the resultant and the centroid. Okay, so let me explain what that means. Okay, so we have R1, we have R2. They're both 9,000 newtons. Okay, now what I'm going to do is I'm going to identify x1 as 3 meters and x2 as 4 meters. Now what are x1 and x2? They are from A, 3 meters, 4 meters. All right? So what I'll now do is say, okay, let's sum up the R's to get a resultant. And let's do this. So let's So we'll plug and chug. And I think you could probably guess what this value is going to be just by looking at the numbers. It's going to be 3.5 meters. Is that okay? So, make it a mess. So instead what I'll do is I'll say, okay, now in the previous option what I did is I replaced every component with a vector. Now what I'll do is I'll say, here's how we're going to handle this. See, the entire load looked like that. And what I'm going to do is replace all of it with this, such that this distance is 3.5 meters. So instead of dealing with each individual component, let's just use the whole thing. Okay? And what's going to happen? Well, let's see. If I sum moments at A, I'm going to have, what is this, negative r times x bar plus by times 6 meters equals 0, right? R times x bar, by times 6 the other way. So therefore, by I get the same thing that I got before. Make sense? And then I can go through and do the other one. I mean, we know what's going to happen. I can say, all right, let's, I'll do this quick. AY plus BY minus R equals 0. We get that. Not too bad, right? Either way works, okay? The main point of this example, to be honest, I think the math is really easy, but the main point of this example is to illustrate the connection between centroids and statics. And the idea that you could use the centroid as a means of simplifying problems, but still maintain static equivalency, okay? That's sort of the point. And that either way works. Okay. So does anybody have any questions on this? Okay. So what I'm going to do, I've got homework for you. I've got two problems. The first problem is I am actually having you compute the location of the center of a truss, or centroid of a truss. And then I am giving you a structural analysis problem involving a distributed load. Okay. Just so everybody's aware as to where this is going, so here's what we have left in the world of centroids. Well, we really only have one thing left in the world of centroids, and that is this. How to compute the centroid of a volume. Okay? Very not a civil engineering problem. You're welcome, MEs and BMEs. This is very, very not civil. But I do like this problem because the challenge with this problem is not the math. It's the bookkeeping. Okay? Then what we'll do is we're going to take a step back away from centroids. We're going to look at something called a moment of inertia. And the reason for that is because the algorithm to compute a moment of inertia uses centroids, and you'll be doing that a lot later in your engineering careers as well. Okay, that's all I got, everybody. I will see you.